So, you've done it. You've built a powerful classification model, and that's fantastic. But here's the million-dollar question. How do you really know if it's any good? Today, we are going to dive into the essential metrics you absolutely need to understand to evaluate your AI so you can actually trust the decisions it makes.
And yeah, that's the core question, isn't it? You poured all this data and time into your model, but without the right evaluation, it's really just a black box. How can you be sure you can rely on what it's telling you?
To make all these concepts really stick, we're going to use a simple but, high-stakes example. We're going to build an AI model to detect sharks in the ocean. This is going to help us understand what each of these metrics actually means when it really matters. Okay, let's get into it. Everything, and I mean absolutely everything when it comes to model evaluation, boils down to just 4 possible results when your model makes a prediction. Let's break them down. First up, we've got the true positive. This is the heck yeah moment. There's a shark in the water, our detector goes off, and it's right. The prediction is positive for a shark, and that is true. Perfect. Next, we have the true negative. This is also a huge success. Our detector sees some harmless seaweed float by, correctly says, nope, not a shark, and stays quiet. The prediction is negative, and that's also true. Another win. Okay, now we get to the errors. A false positive is basically a false alarm. Our detector spots a big old tuna, gets spooked, and yells shark when there isn't one. The prediction was positive, but it was false. And finally, we have what's often the most dangerous error of all, the false negative. A real shark swims right past the camera, but our model is asleep at the wheel and predicts no shark. The prediction was negative, but tragically, it was false. This is a huge missed threat. So with those 4 outcomes in mind, you might be thinking, hey, the easiest way to measure this is just to see how many it got right overall. Well, that's called accuracy. And as we're about to see, it can be seriously deceptive. Now, accuracy is super intuitive, right? It's just the total number of correct predictions, that's our true positives plus our true negatives, divided by all the predictions we made. It spits out one simple percentage. And let's say our brand new shark detector has an accuracy of 99%. Wow, that sounds incredible. We should probably roll this thing out to every beach in the world, right? Well, maybe not so fast. Here's the catch. What if sharks are super, super rare? If 99% of what our camera sees is just empty water, a lazy model could just predict not a shark every single time. And guess what? It would still get 99% accuracy, but it would be a complete failure at its one important job, finding the actual shark. This sneaky problem is called class imbalance, and it's a trap that pops up all the time in real-world data, from finding fraudulent transactions to spotting tumors in medical scans. And this is exactly why accuracy, even though it's easy to understand, is rarely the main metric you'd rely on for a serious project. So, if accuracy can totally fool us, what should we be using instead? Well, we need to pull out a more specialized toolkit. And that toolkit contains 2 of the most important metrics in all of machine learning: precision and recall. Think of these 2 as looking at your model's performance from 2 very different and often competing angles. There's a constant trade-off between them, and understanding that is absolutely key. Let's start with precision. The number 1 goal of precision is to minimize those false positives. It wants to be absolutely sure that when it raises an alarm, it's for a good reason. It hates being wrong. Now, on the other side of the coin, you have recall, which you'll sometimes hear called sensitivity. Its focus is the complete opposite. Its main priority is to minimize those dangerous false negatives. It wants to find everything it's supposed to find. And these questions right here get to the heart of it. Precision asks, of all the times we yelled shark, how often were we actually right? Recall asks a different question. Of all the real sharks that were actually out there, how many of them did we manage to spot? So one is about the quality of the alerts. The other is about the completeness of the search. So which one do you choose? Well, it all depends on the job. You'd want to maximize precision when false alarms are really expensive or annoying. Think about a fraud detection system that locks someone's credit card. You want to be pretty darn sure before you cause that headache. But you'd maximize recall when missing a case would be a catastrophe, like in a medical diagnosis for a serious illness. You'd much rather have a few false alarms than miss a single real case. Okay, but what if both are important? What if you can't afford a ton of false alarms, but you also really can't afford to miss any real threats? That's where we need a metric that can strike a balance between the two.
And that brings us to the F1 score. Think of it as the diplomat that brings precision and recall together. It's a clever metric that combines both of them into a single score. Because it's a harmonic mean, it really punishes models that are terrible at one metric, even if they're great at the other. This makes it a fantastic go-to metric for those tricky imbalanced data sets we were talking about.
So we've got all these individual numbers flying around, but how do we see them all together in one place? How do we get like a complete dashboard view of how our model is doing? Well, it turns out that all of these metrics we've discussed, accuracy, precision, recall, even the F1 score, they're all calculated from one simple but incredibly powerful table, the confusion matrix. And here it is. The confusion matrix just neatly organizes those 4 outcomes we started with. You can see the actual real-world truth on the rows and what your model predicted in the columns. So right away, you can see where your model is succeeding. That's the diagonal line with the true positives and true negatives. And more importantly, where it's getting confused. It's the ultimate source of truth for your model's performance. The matrix is awesome for getting into the nitty-gritty details, but sometimes you just need one single picture to see how good your model is at telling things apart overall. And for that, we turn to the AUC-ROC curve. It sounds complicated, but it's really just a powerful graph. It plots how good your model is at finding true positives versus how often it accidentally creates false positives. Basically, it's a visual report card on how well your model can tell a shark from just a fish. And the best part is, you can summarize this whole beautiful curve with a single number, the area under the curve, or AUC. This number goes from 0 to 1, and it's simple. The closer your score is to 1, the better your model is at separating the classes. A score of 1 means you've got a perfect model. So, as we wrap up, I want to leave you with this one critical question to ask yourself on your next project. Which type of error would be more costly, a false alarm or a missed threat? Your answer to that question will tell you exactly which metric you need to focus on. Thanks for tuning in.